Now, since we have defined work and got the formula finding work by a constant force, it's time to see how we can find out the work done by a variable force that's changing as a function of position of the particle on which the force is acting. So let us remember the formula once again about the work done by a constant force. This formula is work done by a force given by force vector dot product displacement vector, and now that is given by force magnitude into displacement magnitude into cos of the angle between these two vectors, where F and S are inclined at an angle of theta between them. This is my formula 1 that we have done some time back. So this formula is all right when we see the body is moving in the direction of the force. Say, let us consider a situation with this figure. This is a straight line, horizontal straight line to the right, and we take it to be our coordinate system where we take this as the origin and this is the positive x direction, and suppose a block, this is the particle that is initially at this position and finally it has come somewhere here. This is the final position. Okay, so we know how to just define the x coordinate of this particle. Initially, suppose this distance is x1, so the corresponding x coordinate of the particle is x1, and later it has gone here. That means measuring from the origin where x is equal to 0, this distance is say x2. So we write down the corresponding x coordinate of the particle, that is the block here. I have told already that you can treat this block as a particle and you can take the center of mass roughly to be its position. In translational motion, we can consider a body of extent as a particle for convenience. And here, of course, this is the origin, that is x is equal to 0 here. Now, the displacement of the particle in such a case is given by, let me show it. Displacement of the particle is delta x, that you find by subtracting the final position minus the initial position. So delta x in the rightward direction, in the plus x direction, that is given by final x coordinate minus initial x coordinate. If the force acting on this block, that remains constant in magnitude, of course direction is constant because the force is acting in the plus x direction, the same direction of displacement here, displacement vector, that's in plus x direction, force here also in plus x direction throughout. So obviously the theta here is 0 degree and cos theta is 1 between the force and displacement vectors. But I have said, suppose the force also remains a constant in magnitude. In that case, work we could find straight away from this equation number 1 above to be, work was found to be the force, that is the constant value, and displacement, that is delta x, that's the magnitude, into, since f and delta x, they are both pointing in plus x direction, this is coming out to be cos 0 degree, and we just can conclude that the work done by the force is f delta x. That's a simple situation where the force remains constant in magnitude as well as direction, and displacement is parallel to the force at every single point. But the question is, if this force, maybe it maintains a constant direction, that is in plus x direction, so the angle remains of course 0 degree, but the magnitude part of the force is changing with as a function of position. In such case, how to find out the work done by that variable force? That is our discussion point today. I'm just saying that this force is no longer assumed to be constant in magnitude, although the direction remains constant to the right in plus x direction. And this force is found to be a function of x, say, the position of the block. It may be in any form. This force may be given as maybe something like ax square plus bx plus c, where a, b, c are constant, or in a simple way this force can be given as say minus a constant k into x, as we'll see in the case of a spring. So these cases are all considering different possibilities where the force varies as a function of the block's position and direction remains always to the right. In such a case, we want to find how we can apply the formula learned earlier to get the work done by that such a variable force. That we shall discuss now. Now let us take one more look at the figure itself and try to see the work in front of us. Say at any variable case, like at a given instant, the block is somewhere in between its initial and final positions, and that I show by this blue dot. The block is somewhere here. I have just shown a point. This is a particle, I have said, and this distance measured from the origin, that is O, is given by x. This is the x, and since I said the force itself is a function of position of the block, you can simply guess that the magnitude of this force F is some value at x1, the starting point. Then as the value of x is a variable value of x, it continually changes from a lower value of x1 up to a max value of x2. And as the block proceeds along this path, at every single point on the path as the block moves, the value of this x is continually changing. And if x is changing, since force itself is a function of position x, so force also is changing in magnitude. So we can't really find out a simple formula like F into delta x or F into s. What you need to do is that we have to take a very small interval here, a very small displacement, assume that the force remains constant over that small position interval, get the product, find the small bit of work over the small interval, and add it up for all those small intervals which add up to give you x2 minus x1, delta x quantity. Once again, what I said, looking at the figure, you see that as the block is moving from x1 to x2, the value of this x, that is position of the block, as measured from the origin, that is continually changing as the block advances. And accordingly, the value of the force also, magnitude, is also changing continually, whatever be the function of the force is as a function of x, but is changing. So since F is continually changing, what we need to do, we need to pick up a very small interval of space here along this path and assume that over that very small interval, the value of F remains constant. Find the work done by that force over the small space interval and add up all such infinitesimal works in calculus language to find the total work done in moving the block from here to here. I shall have a more elaborate figure and see the application of calculus integration to discuss this problem from now. So we have on our screen the earlier figure, of course, redrawn. As you can see, this is the origin, a block moving in the x direction under a force of F. Initial position was x1, final is x2, so that displacement is delta x. This delta x, of course, is given by...
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.